All the bottles are gonna dry, just like the cheeks under your eyes. But they won't stay like that for long. All the gasoline will last, and you look at all this mess. It seems so big now that they're gone.
All right, folks, thanks for joining us for the faux interview. I am trying to figure out how to add Jeremy and Diane, so just give me a few seconds and we'll get going with the faux interview.
But now we're falling underground, making noises for the background. And the lonely town is staring at the foundation and wondering if that's the crowd. It's something crazy. I can see the world right outside, but I'm too tired to hide.
All right, are we
Okay,
getting?
there we go.
Hey, it all worked.
Hey, woohoo! Now we just need to wait for Jeremy, I guess.
Awesome, awesome. In that case, I'm gonna blast our 11 viewers with some additional punk rock
Okay.
straight from the copyrights. This is from their latest record report. This is called Heart of Glue. Awesome, awesome. All right, we got Diane and Jeremy on the line.
Hi, guys.
Awesome, cool, cool. Well, looks like we just lost Jeremy. Well, I'll get in the hood. Let's go ahead and get started while we're waiting for Jeremy to join up. So I'd like to welcome everybody to round 2 of the faux interviews for Lady Storm Hackathons. I'm subbing with the very capable Cassidy Williams and Amy Chen today as your faux interviewer. My name's Rob Spectre. I have the privilege of serving as a developer of phone calls right from the apps that you're already building from the languages that you already know. So today we are going to be faux interviewing 2 computer science students, Diane and Jeremy. Diane, why don't you introduce yourself to the crew?
Yeah, so hi, guys. I'm a junior at Harvard studying computer science, and I don't know, what else do people usually say here?
So you're studying computer science at Harvard. What's your language of choice? What's the last thing you built for fun, and what are you looking to get out of today?
Okay, language of choice is Python.
Yes.
Although I am kind of partial to OCaml, which is this really obscure functional programming language. And let's see, something I built for fun is a Bayesian classifier that helps detect emails that mention free food.
Oh, that's rad. I was so excited about using Python, my browser crashed. That's how excited. And it seems like Jeremy's running into a little trouble indicating that he keeps getting a server error, so we're going to try to get him to join
Okay.
via phone call. Does anybody know how to do that? How does that work? How does the thingy work? I'm just gonna keep clicking things. That's what I'm gonna do. Nothing terrible ever happened as a result. Ooh, I think I know what we can do. I think we can just call him, right?
Sure, let's go for it. Yeah, I'm not that familiar with Google Hangouts.
Oh, there's like a jillion Jeremy Myers on Google Plus. Stay on target. Jeremy, win. Jeremy. Oh man. This
Hello, can anyone hear me?
Hello?
Hello? Is it working? Can you hear me? Hello, can you hear me?
Yes, indeedy. I can totally hear you. Can you guys hear me?
Yeah.
All right.
Woohoo!
Okay. Nobody touch anything. And hopefully this will work for a little bit. Groovy. Let's try to kick this off again. Diane, we heard from you. Harvard computer science major who made a handy hack to get some free food. Jeremy, why don't you introduce yourself?
Yeah, my name's Jeremy, and I'm a computer science student at Purdue, senior this year. Made a couple different hackathon hacks. Currently, last one we made was Boilermake. We made a hackathon Tinder app, so you could like kind of like swipe left or right for people to be on your hackathon team. Yeah.
Awesome. Awesome. That sounds like a lot of fun. Cool.
Yeah.
Well, today we're going to be hacking a little bit in Python, and we're going to be covering some abstract data types, specifically stacks, queues, graphs, and trees. So, what would you two like to get out of the next 45 minutes in this phone interview?
Just practice. I'm down with practicing anything.
Groovy. Jeremy, how about you?
Yeah, same here, I guess. Yeah.
Okay, righteous. Well, let's go ahead and get stop with the yakking and get with some hacking. So, as you can imagine, working at Twilio, where we're sending text messages and making phone calls all day, every day, queues are very near and dear to my heart. So, how about we kick off there? Does that sound like fun?
Sure.
Great. So let's start with some definitions. We're going to be working with stacks and queues first. So first, what is a stack? Oh my God, Jeremy, you are the best dressed person in this interview.
Yeah, it's
That is A+. Oh, that's great. Cool. So let's start with you, since you have the tomato red T-shirt, Jeremy. What is a stack?
All right, so a stack is pretty simple. It's basically a data structure you can use to store things. You want to put them in one at a time, and then whenever you put in the last item, you want it. So essentially, it's like last in, first out. So when you pop something from the stack, you want it to be the last thing you put on it. So it could be like a stack of pancakes, and you take the top one off first.
I like that. I like the pancake analogy. That's very bold. Okay, Diane, so what are some operations that a stack can perform?
Pop and push. So pop means that you take something off the beginning of the stack, and then push means you put something at the end.
Is it the beginning of the stack or is it the top of the stack?
Oh, sorry. Did I say stack? I meant queue.
No, stack.
Oh, sorry. Okay. Forget about what I just said. For a stack, so you want to push something onto the top of the stack and pop something off the top.
Okay. Does that break the last in, first out? Does that break the last in, first out operation that Jeremy was describing?
Wow.
So when you say you pop something off, where in the stack does it take it off from?
From the top.
From the top. Okay, not the bottom. But
Yeah.
Gotcha. Cool. What are some other operations that a stack can perform? Let's be open to the both of you.
You peek, so you just want to look at the top.
Yes, peak. Peak is an important one. Also called top. That's one. What are a couple others? Well, you can swap, right? Swap is a common one. You can take the top two items and reverse their position in the stack. That's a big one. Okay, cool. Let's move on. Let's move on to queues. So we have the stack as a data structure where it's last in, first out. What's a queue all about, Diane?
So that one would be first in, first out.
First in, first out. Okay. What are some operations that a queue can perform?
So similar to stack, it also has push and pop, but they behave a little differently. So
how differently do they behave, Jeremy?
Right. So the idea is that with a queue, if you're like standing in line to maybe buy a Starbucks coffee, right? So things come in the background.
You were doing great with pancakes. You totally messed up with Starbucks.
Did I? Darn. Well, okay, so the way a queue works is if you imagine a queue as having like a front and a back, then you will push things into the back of a queue, but you will pop them from the front of a queue.
Gotcha. What are some other operations that a stack can perform? Or I'm sorry, a queue can perform.
So I guess a queue can also peek. You could look at the next item, and that would be from the front of the queue.
Is it peek or is it front?
Oh, I guess it depends on your language. I don't know, but yeah. So really, you're looking at the front of the queue. So maybe it's
Uh-oh, we lost him.
Oh no! Oh no!
Yeah, just 1 second. Sorry about that.
Oh, there he goes. Well then.
Womp womp. Diane, what's another important operation that a queue should
I guess you should still be allowed to swap things, just like for the stack.
Well, that can get a little complicated, but what are a couple things like a couple bits of information that a consumer of a queue is basically always going to want to know, like especially around like the items that are inside it.
Maybe the length of the queue?
A size of the queue? Yes, that's totally one. What's another?
Uh, hmm.
Maybe something Boolean about the current state of the queue?
Oh, if it's empty.
There we go. Totally. That's another important one. Well, while we're waiting for Jeremy to come back, let's take a moment to compare and contrast. So we've defined what stacks are. We've defined what queues are. What are some examples of stacks in the software that you use today?
Examples of stacks. Well, for example, in function calls, that uses a stack. So if you, for example, recursively called a function, that would be building up a stack of stack frames.
Okay. What are maybe some more like tangible examples like of you using a piece of software and identifying that the author clearly used a stack implementation here?
Let's see. I think I'm getting a little stuck here.
Okay. Well, what's a piece of software? What's a piece of software that you use to join this Hangout that might have a stack implementation in it? Maybe your browser with your browser history? Would that be an example of a stack?
What aspect of it, I guess, is what I'm getting stuck on.
So your browser history, might that be an example of a stack?
Oh, yeah, that makes sense. Yeah, because as you visit new pages, you'd add things to the stack, and then as you press the back button, that would be sort of like popping things off the stack.
Awesome. Welcome back, Jeremy. We were just talking about real-life examples of stacks in software that you currently use. So what would be an example of some software that you use today where you could observe a stack data structure being used?
Okay, so examples of stacks.
Can't hear you. I think you're muted, Studley.
Can you hear me now? Hello? Any sound? Hello?
Still can't hear you, big guy.
Okay.
Okay. Well, doesn't look like we're gonna be able to hear Jeremy, which is a shame because he has that excellent baritone.
Can you hear me all right now? No.
Oh yeah, plugging in the headset. I feel like this is gonna work. I feel it. I feel it in my heart. Uh, okay, so here's the bad news. Like, my cell service has not been great in here, but we're gonna give this a try. Oh no. Ugh. Well, I think what we're gonna have to do here is go ahead and move on without Jeremy and just put you in the seat by yourself. Is that gonna
Okay.
be?
That's fine.
My cell calls all this afternoon have been dropping in Brooklyn, so things going on with AT&T. Jeremy, we're very sorry, sir, but looks like we're gonna have to press on without you in this case. So, practical examples of queues. What are some examples of queues in the software that you use today?
Hello?
Hello?
Oh, wait, I have Jeremy on speaker. Can you hear him? Wait, Jeremy, say something.
Hello, yeah, this is Jeremy.
Can you hear him, Rob?
I can.
Okay, we'll try this.
Wow, this is amazing.
Okay, examples of queues in real life software. Well, like, for example, when you try to call like your bank and then they put you on hold, then they put you in a queue, and whoever called earlier will get off the queue earlier than you.
Gotcha. Totally. Jeremy, what are some ideas of software that you use today that uses a queue?
Hold on, wait, Jeremy, did you hear that?
No, I don't think I can hear Rob. Hold on, let me see if I can get on the line.
Okay. He asked you for examples of queues in real life software.
Okay, so, right, so an example of a queue, so, let's just talk a queue. Right, so if you like, if you're trying to sign up for a new beta program, like, then usually they just let you sign up in order, so, like the first person to sign up gets the first, like, so forth, all they have.
Cool. Totally. Right on. Well, why don't we take these two concepts and mash them together and write a little code. So this is a common interview question. You're probably going to get it in every prep book that you ever pick up. But the idea is to implement for the interviewer a queue using two stacks. So you have two stacks that you manipulate, and you implement a queue using those two. Why don't we go ahead and give that a shot? Does that sound good?
Yeah.
Okay, cool. So what do we need to do first here?
Let's see. Well, first let's just talk about the overall idea before we dig into the code. If that sounds okay to you.
Sounds great.
Sorry, one more sec. Jeremy, can you hear things now?
Yeah, I can hear kind of. I think I answered the question though.
It's implement a queue using two stacks. Or did I get that backwards?
Yes, implement a queue using two stacks.
Okay, yeah. So implement a queue using two stacks.
Okay, sure. So maybe the way I would think about this first is, so what happens when you have a stack and you push something to it, right? And so, like, you push three things. And so you'll have the first thing on the bottom. And then what you want to do is you want to return that first thing. So it's kind of like it's reversed, right? The idea is that things on the stack are
backwards from where you want them, whatever you want to PhD with, or like whatever you need to do, because it's actually stacked. The first thing we want to do is probably like, I don't know, maybe like reverse the stack every time you want to remove something, maybe?
Or like, yeah, whenever you want to remove something, just pop things off of the first stack and push it onto the second stack, and then pop the top thing off of the second stack.
What do you think about that, Jeremy?
Yeah, that sounds like it would work.
Why might Diane's suggestion be preferable to the initial implementation that you suggested, Jeremy?
Sorry, what's the question?
I think we're having some audio issues. So basically, he asked you to compare my suggestion versus your suggestion.
So the way I see it, they're kind of like the same suggestion. Right? So the idea is that by pushing everything from one stack onto another stack, you're effectively reversing the stack. And so that's all I was.
Are you necessarily reversing the stack, or are you producing the behavior that you are looking to produce? So to put it another way, which of the two approaches do you feel would be more computationally expensive?
So I think it really comes down to if you have, so it's like when you push an item onto the stack, if you wanted to be able to do that in, in constant time, so if you push it on and it just happens, right? Then you would always need to have that stack, and so every time you pop an item, then you have to push everything onto the second stack, pop the item, and then push everything back onto the first stack in order to keep the pack of the queue open, I guess. Right? So the idea is it would take 2n times, where n is linear, and that's kind of just the number of items that you've already got there, just to remove an item. And yeah. So that takes some time, right? It takes longer than if you could just access that item at the moment.
I didn't really hear it, but it sounded like he was suggesting because we had 2 stacks as opposed to 1, we had more memory overhead. Is that what he was suggesting?
No, I think he was talking about the time complexity of like having to take everything off of the first stack and then put everything onto the second stack, and how so if you wanted to take something off a normal queue, usually that would take constant time. But since you have to move everything in the queue, like to the other stack before you can take the top thing off, then that changes it to linear time.
Okay, but the part of having to perform a reverse on the stack with each member that gets added to the queue, do we feel that that could become a problem as the queue size grows?
Wait, yeah. Yeah, definitely.
Okay, why is that?
Just because the more things you have in the queue, the more things you're going to have to like reverse.
Right. And performing that operation is going to be pretty expensive once it gets past a certain size, right?
Yeah, you have a really big queue.
Cool. Cool. Well, let's give the 2-stack option a try then. If we feel like it may be the more efficient approach compared to reversing a single stack. So we got 2 stacks. We're gonna take an item off one, plop it on another every time. we try to dequeue a member from the queue. How would we set that up in Python? How would we set that up in a queue that we would want to consume?
Yeah. So what I might do is I would first define the stack class, and then define another class called define the queue class, and then make that be based off of 2 instances of the stack class.
All right, let's see that. Let's see that in action.
Okay. Oops. So I want to define hop. So if we want to, oops, we don't want to put. Okay. So if we want to pop something off the stack, then we'll just yeah, I think we can literally just do that, or return that. And then if we want to push an element onto the stack, we can do let's see, stack. Insert 0 else. Okay. So I think that's what we need for what we need from this stack class.
Okay, Jeremy, do you want to implement the queue?
Jeremy?
Yeah, sure. Right, so the way we might have the queue is you would want, we can maybe have, 2 stacks. So we'll have one stack that represents the items, and one that can be the auxiliary stack for reversing. So let's call this self.stack equals stack. And I think in Python we got this, or is it stack?
No, you can actually just do that.
Right, okay. So then we also want self dot, let's just call it an auxiliary stack. Also a stack.
How do we feel about those names, guys? It's an important part of programming. It's the hardest part of programming is naming things.
Let's see.
What are the 2 stacks doing?
What are they doing?
Yeah, what purpose are they serving in the queue that we're implementing?
Basically, they let us access the beginning or the end, depending on which stack our elements are currently in.
Well, or to think about it another way, in the manner that you were describing before, Diane, is one stack for receiving and one stack and another stack for emitting?
Yeah.
So with that in mind, how might we adjust the way that we're describing, the stack and aux?
Um, we could rename them to like to borrow your words. We could rename them to maybe receive and emit.
Maybe. Be good. Looks like Jeremy's going to town. Can you describe what you're doing, Jeremy?
Sure. So the first thing I was thinking is that this stack here is called stack right now. This stack is just going to hold the items in a normal stack. And so the idea here is that when we queue an item, we just push it onto that stack. Now, when we need to, it's a little trickier because since we just have a stack of items, whenever we actually want the item on the bottom of the stack. But to get to that item, I'm thinking we just reverse the stack by popping everything off of our stack, pushing it on the auxiliary stack until that stack is empty. And then we can just pop that bottom item off. Now it's the top of our auxiliary stack. So by popping from one stack and pushing to another stack, we can reverse the item. So we can get the bottom. And then when we're done, we can push everything back onto the original stack, and we keep that stack order so that every time we add an item, it's just going to be added to the top of our original stack.
Diane, what do you think about that?
Oh, sorry, I was kind of zoning out trying to make sure the sound was working. Sorry about that.
So, Jeremy, we want to explain to Diane again what you're trying to implement here?
Right. The idea is that queuing, we can just push onto our stack. But then we need to. What we want to do is reverse this stack using our auxiliary stack. We want to pop the bottom item off because the stack holds the item in the wrong order, so we need to reverse it. We pop off that item. And then we reverse it again, so that way queuing can just be pushing to the stack. Does that make sense?
Yeah, that makes sense.
Okay.
That sounds like it'll produce the correct results to me.
Sure.
Okay, Diane, I can tell you want to point out some syntax stuff here. Go ahead.
Yeah, just a tiny little typo. Oh, yeah. Just little things.
That's not the only one you see, too, right?
Yeah. And then I'll go ahead and fill in size.
Nice. Work. Oh, let me scroll. I think what Google Docs does to Python indentation is criminal. Okay. So we got a reverse stack, we got an unreverse stack, but we're kind of missing something on these two functions. Do we want to perform a mutation on self, or do we want to return something else? Okay, so we have two approaches here for the reverse stack and unreverse stack functions. What we have implemented first is an adjustment of the stack and aux attributes that we have declared in our constructor, or we could produce a function that instead returns the change stack. Right?
Mm-hmm.
Why would one be preferable to the other? Why would we want a return statement as opposed to adjusting the attributes of the object?
So I think I can see a reason. So
What's
here, the way I set it up originally, we're reversing the stack, and this does mutation. So we have to unreverse the stack. But if we were to just return this data from the reverse stack function, then we wouldn't really need to unreverse the stack because assuming that we do no mutation to the original reverse. Right?
Winner, winner, chicken dinner. That's totally correct. Yeah. And what's another benefit that it would have, Diane? Would it be a lot easier to test? Yes, it would totally be easier to test because then all we would have to do is assert against the output of a function as opposed to introspect a data object that we create. So it would dramatically reduce the complexity not just of the operation that we're trying to perform, but also would reduce the complexity of the test that we would ultimately write to see if that code does what we would expect.
Mm-hmm.
Why don't we give that a try right quick? Diane, you want to adjust this? You want to adjust this implementation to use that technique?
Sure.
Cool. Okay. Do we need unreverse stack for this operation? Is there a way that we might be able to make this reverse stack function we've declared more generic, so we can apply to.
Sure, yeah. Let me think about that for a sec.
Okay. Well, let's break it down. Break it down.
I have an idea, but it'll involve changing a lot of things.
Okay, let's hear it. Let's hear the idea.
So, I was just thinking that instead of having the two stacks be separate attributes on the class, we just have one attribute that's a list of the two stacks, and then in reverse stack, we would just check which one of those. We would find the index of the stack that has 0 items, and then move things from the other stack to that stack. So like instead of naming a specific stack, we just use indices. If that makes any sense.
Sure. So what might be the problems with having them both in the same list, both of the stacks in the same list?
Well, so I thought of something. So I like Diane's answer because that lets us use one function to reverse the stack. But the thing is that you still have to reverse both stacks. I think when you execute. Did you think that's right, Diane?
Yeah.
Okay. Because what I was thinking, so like this is kind of tricky. But what if you don't even change the original self-size stack when you use reverse stack function? So instead, you make a copy of the stack that's already there. So your temp variable would become self-size stack. And then you can just keep track of the number of items. You push them onto the original stack. So you're kind of using it twice, right? You make a copy, and then you use the original one as the auxiliary stack for reverse. Because you've got that size, to make sure that you don't accidentally go too far. Does that make sense?
Let's see it.
Are you guys still there? I can't really hear anything right now.
Yeah, he said let's see it.
Yeah, let's see it.
Okay, well, should I just go ahead and try it out then?
Yeah, give it a go.
Okay. Yeah, I just thought of something. So, I guess the other problem with this idea that I had is that you're still going to have to pop all of the items off of self.stack when you're done. And so it's still going to take the same time as it would to unreverse the stack anyway. So I'm not sure. Maybe it's if we could change our stack data structure, because the problem is that we cannot access any items other than the top items. But that seems to be limiting us.
Are we making that change somewhere, Jeremy?
Right. So the problem is that we don't really. So like the problem with it is that we only have the top item stack. So if we use top, or even like peak to see the top of the stack, it does not let us see any of the other items in the stack. And so no matter what we do, if we reverse the stack, we have to use the other stack. And so since we only have two stacks, and we have to mutate one of them, and then in doing so, we have to fix the mutation, which is only going to take twice that linear time. So I don't think we can actually do this in there's 2n and there's n times. But there's always going to have to be some operation here to fix the thing unless we use like 3 stacks. So yeah.
Okay. Well, let's take a step back a second. We've kind of gone down this road for a bit now. There might be an alternative approach. Sounds like we're kind of getting hung up on terminology a little bit here. Now, Diane, when we first started, you proposed a solution where you would receive items and place them into one stack,
Mm-hmm.
and then when you wanted to dequeue items from our queue, you would retrieve them from another stack.
Yeah.
Right? So with that model, how would you adjust the names that we have for the 2 stacks in our queue? Could we call them in and out?
Yeah.
Okay, let's try that.
Okay.
It changes our thinking on this implementation.
Okay.
Righteous. So, anytime we queue something, we're just going to push something into our in stack, right?
Yeah, I can move right now.
Okay, so what is DQ going to return? Let's go ahead and just reimagine the entire DQ function. What is it going to return? Is it going to return what we pop off the out stack?
Yeah.
Okay, let's go ahead and just set that as the return function then. All right, let's go ahead and kind of get rid of what we've done so far with DQ and just return what's in the out stack.
Like this. This one's going to team.
Okay. Right on. So let's take a look at this stuff here, and just for the sake of argument, kind of remove it for a second. So it might adjust our thinking about this implementation. So we have stuff that's coming in. We have stuff that's coming out. The only issue is the stuff that we're putting in is not in the out queue, right?
Mm-hmm.
Okay. So anytime we return this, we're gonna be returning none, right? Because this is Python,
Mm-hmm.
right? Or it may actually, I'd have to check what happens with pop on an empty list. Let me see. Oh yeah, that actually produces an index error. You can't pop from an empty list. So when we have the stuff on our stack, on our first stack, and we try to return and we get an index error, we're going to know something pretty specific about that stack, right? We're going to know that it's empty.
Yeah.
Right. So maybe to prevent that index error, we can start our function by checking to see if our out queue is empty.
Mm-hmm.
All right, let's give that a try.
So I'll give that a shot. So something like try Um, or is it cache?
Do we have to do a try catch, or is there something built into the queue that we can use? Or well, is there something built into the stack that we can use?
Oh, just check the length.
There you go.
Okay, so if it's 0. Okay, so if we find that the out stack is empty, then I guess we want to try to try to bring stuff in from the in stack.
Yes! Boom! Totally, Diane. How would we do that?
So then we could see. But we'd have to fix our current definition of reverse stack, but basically we could reverse and let's see. So so the size could still be 0, in which case I guess we just return none. So if it's still 0, we can just return none. Else, we
That's smart. Way to anticipate that edge case.
and otherwise you can just pop. Okay, and then as for fixing reverse stack, here we can do. Oh, hold on. And then we don't even need unreverse.
Righteous, what do you think about that, Jeremy?
Yeah, I went ahead and changed.
Oh,
I think we want to reverse in.
Yeah, my bad.
The out stack.
There we go. How do we feel about that, Jeremy?
Yeah, I think it looks pretty good. I think I'm starting to see, the pattern here.
Awesome. And what is that pattern you see?
So the point is that, sometimes you'll have a set of operations, right? So sometimes you're queuing a few items in a row, and sometimes you're dequeuing a few items in a row. And so if you dequeue twice in a row, you don't want to reverse the stack until you're done with all your dequeuing. So the point here is that we only reverse the stack if we need to, right? And then when we use things, we only need to reverse the stack when we have just finished dequeuing things, and now we start queuing. Is that kind of the idea we're getting at here?
Boom! Totally. Spoken like a champion. Cool. Well, awesome, guys. That kind of brings us to the tail end of our time together. Was that useful for you?
Yeah, this is fun.
I got about 10 more minutes to go. if you guys had any general questions about interviewing that I might be able to answer for you for an engineering role. Any overall questions about going to the interview and getting that engineering job?
Let's see. I don't think I have any specific questions right now.
Awesome. Yes. How are you, Jeremy?
I guess maybe what's a good way to practice for interviews? I mean, besides obviously watching these cool YouTube videos that we're making here.
The best thing I think you can do for an interview is learn as much about the company as you can before you go in. So if it is something that you're really interested in, that's going to show through in your interview. And if it's something that you're not interested in, there are plenty of jobs for programmers out there. Maybe you take a look at a different company or a different product, right? And anticipating what that problem domain is going to be is going to tell you what to study for, right? So if you're interviewing for a company like Twilio versus a company like Twitter, maybe you spend more time boning up on your queues and less time boning up on your graphs, right? Because those two problem domains are going to be different. You're going to spend a lot more time actually writing code at Twilio with queues than you are going to at Twitter. Does that make sense?
Yeah, that's cool advice. Thanks.
Cool. All right, any other questions, guys?
I think I'm good. What about you, Jeremy? Anything else?
No, not that I can think of.
Well, Jeremy and Diane, thank you so much for your time. This was a whole lot of fun going down the Q path with you folks. Also like to give thanks to Amy Chen and Cassidy Williams for, again, putting together this excellent program for Lady Storm Hackathons. And you guys should tune in to the Facebook group for more information on when the next round is going to be, and to volunteer for you yourself to sit and share the faux interview process with your peers. So thanks a lot, guys, for having me out, and I will see you at the next hackathon. Take it easy, guys.